All right, welcome to part 2 here, talking again about right triangle trigonometry, focusing on the trig ratios here. I want to take a moment and just briefly introduce this idea of the trig functions. So we're going to be calling them the sine ratio, cosine ratio, tangent ratio. But we also have these expressions or equations that we write that involve what are called the trig functions. So we abbreviate them SIN, COS, TAN, depending on whatever. But this right here is a function. It's an operation. It takes an input and it gives us an output. And so this right here is our trig function sine, SIN. It takes an input here inside of these parentheses, like many operations, square root, whatever operation you can sort of think of. It takes an input, and that input is an angle. Either the name of an angle, or we're going to see later on in the chapter actually an angle measurement. And this is our input. Again, it's either the name of a particular angle, or later on we'll talk about it as a measurement as well. And it gives us an output. This here is our output, and it's the ratio. For sine, that would be the opposite side divided by the hypotenuse. If we're plugging in an angle value, an actual measurement, our calculator will give us something like a decimal version of this fraction, won't necessarily give us a fraction, right? If we do, I don't know, the sine of 40 degrees, let me use parentheses with that. You don't have to, but important. So sine of a particular angle measurement, it's going to give us an output, and that output is the ratio. This ratio is expressed as a decimal, but, you know, fractions and decimals can be expressed as each other. But anyway, so it's an important idea of understanding how these things work and how these trig things are actually a function, an operation that's being performed on an input, an angle, either the name of an angle that we can see in a picture and we can give the ratio of the sides, or an angle measurement where we can actually get, you know, a value out here. And so this can be for the same for sine or cosine or tangent, all of these things in there. This is an important idea. We'll touch on it a little bit more as we get further in, but I think just wanted to talk about this kind of notation and the way this looks. All right. So here we're going to look at example 2. We're going to identify some trigonometric ratios. I have our SOHCAHTOA mnemonic device written out here a little bit of a different way. This is a little more of a visual way of seeing the different things, right? That sine is equal to opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Anyway, let's go ahead and take a look at this example here. So we're going to be identifying the trigonometric ratios for this triangle. We're doing the sine of angle A, the cosine of angle A, the tangent of angle A. So all of these are using angle A. So I can go ahead and label my triangle sides relative to angle A. So I'm going to label opposite, adjacent, hypotenuse. So the opposite side is going to be right down here. That's across from angle A. That's our opposite leg. Just going to go OPP for that. Our adjacent leg is going to be the leg that is next to that angle. The leg, not the hypotenuse. So this is our adjacent. And then finally, the hypotenuse. The hypotenuse is always the longest one. It's always across from the right angle here. So this is our hypotenuse. All right, so let's go ahead and identify what these particular ratios will be. So the sine of angle A is opposite over hypotenuse. So that's going to be 20 over 29. Easy enough, just the ratio of those two particular lengths. The cosine of angle A is going to be the adjacent over the hypotenuse. So that's 21 over 29. And then finally, the tangent of angle A is going to be the opposite divided by adjacent. So 20 over 21. There we go. Those are our three ratios. Now, really quickly, this was relative to angle A. We could also be asked some very similar questions, but relative to a different angle. And we can see how these change a little bit. So sine of angle C, we can actually use angle C instead. And I'll go ahead and write all those out really quick. At this point, please try to pause and see if you can identify these different ratios relative to angle C. All right, so for angle C, what changes, right? What changes? The hypotenuse is the same, doesn't change. Hypotenuse is across from the right angle, doesn't change. So the hypotenuse is the hypotenuse. But angle C, the opposite and the adjacent actually switch places. This leg that is now opposite of angle C is this one over here. So this side is now my opposite. And this side, which used to be the opposite, is now adjacent. It's the one that is next to angle C. So this one is now my adjacent. So they actually just switch places. Easy enough. So the sine of angle C is now opposite over hypotenuse, 21 over 29. Notice this. The sine of angle C, 21 over 29, is actually the same thing as the cosine of angle A. Think about why that would happen. Cosine of angle C, that's going to be adjacent, 20 over hypotenuse, 29. Notice this, cosine of angle C is the same as sine of angle A. Coincidence? Maybe not. Tangent of angle C, tangent is opposite over adjacent, so that's 21 over 20. Is that related to anything? Is that similar to anything in this realm? Maybe, maybe not. Take a look at these two. All right, we're going to continue this idea again. Feel free to pause and work ahead, and then just kind of check in with me what we're doing here. So we're looking for the sine of angle Z. So sine is opposite over hypotenuse, angle Z. So this one over here is our opposite. It's across from the angle, and then across from the right angle, this is our hypotenuse. So the sine of angle Z is equal to 12 over 37. Moving forward, let's go ahead and do this next one. Tangent of angle Z. So tangent is equal to the opposite divided by the adjacent. Angle Z is right here. So the opposite is over here. The adjacent is right here. 21 over 20. And then finally, the last one here, cosine of C. So here's our angle C. Cosine is adjacent divided by hypotenuse. So the adjacent is the leg that's next to your angle, leg that's next to, so that's adjacent. And then the hypotenuse is across from the right angle here. So this is my hypotenuse. So that's 40 over 41. There we go. Now you can see here we have some more practice problems of identifying these ratios. Again, feel free to pause and sort of work ahead. I'm going to run through these here relatively quickly. All right. So for number one, we're using this triangle. We're going to identify the sine, cosine, and tangent of angle P, and then we're going to switch that and look at angle N. So I'm going to start with angle P. That's right here. This side over here, 9 is my opposite side. Right here, this one is the adjacent, it's the leg that is next to it, and then our hypotenuse is over here. Sine is opposite over hypotenuse, so that is 9 over 15. Now this does reduce. We could simplify this if we want to. Generally, when we report fractions, we would like for them to be in simplest form. So I'll go ahead and do that. These are both divisible by 3, so that's 3/5. So 3/5. Cosine of angle P, cosine is adjacent over hypotenuse, so that's 12 over 15. Again, this also reduces. These are also divisible by 3, so this is going to be 4 over 5. And then finally, tangent of P, so tangent is opposite over adjacent, so that's 9 over 12. Again, this is reducible. These are also divisible by 3, so this simplifies to be 3/4. There we go. Those are our 3 ratios for angle P. We're going to go ahead and take a look now at angle N. So angle N changes things a little bit. Remember, now this side over here is now the opposite, and this side here is now the adjacent. Hypotenuse is still the hypotenuse. So the sine of angle N is opposite over hypotenuse, that is 12 over 15. We already saw that ratio, right? That was the cosine ratio of the other angle. Again, this also reduces 4 over 5. Both divisible by 3. So 4 over 5, again, same as the cosine of the other angle. That's a relationship that always happens. We'll see that through and through, but the cosine of one angle is going to equal the sine of the other angle within the same triangle. So actually we could use this to predict. This one is going to be 3/5, but let's go for it. Adjacent over hypotenuse, 9 over 15, which is 3/5, right? Those both divide by 3. And cosine of n is the same as sine of p. We already talked about that. And then finally, tangent of n, that is going to be the opposite over the adjacent, 12 over 9. Both of those are divisible by 3, 4/3. I didn't really talk about tangent, but notice these, the tangent of one angle and the tangent of the other angle, they do have a relationship. They are reciprocals of each other. So tangent of p was 3/4. Tangent of n is 4/3. They're reciprocals. All right, here is our last problem, a little bit of a tricky one. We're given one of the trig ratios and we're asked to find the other one of the same angle. So we know that the cosine of angle A, so cosine of angle A is equal to 5 over 13. Cosine is adjacent over hypotenuse. So relative to this side or this angle, this side over here is our adjacent and this side over here is our hypotenuse. And then this one's the opposite. This ratio is telling me 2 of the side lengths that I have. It's telling me that my adjacent is 5 and my hypotenuse is 13. I want to know what the sine of this angle is. In order for me to know the sine, I actually need to figure out the opposite side, right? Because sine is opposite over hypotenuse. And I currently don't know what that is. What can I do? Well, we have a right triangle. We know 2 of the sides. This is something we've done a lot. Pythagorean theorem, right? Leg squared plus, we'll call this one x, leg squared equals hypotenuse squared. So 5 squared plus x squared equals 13 squared. Let's simplify this. We'll solve it here. I have x squared is equal to 144. Take the square root of that, get x equals 12. So my opposite side here is 12. Picture's not quite drawn accurately. These kind of look like they're switched, but that's fine. We're just using the picture for guidance here. So the sine of angle A equals the opposite, which is 12, divided by the hypotenuse, 13. So given one of the trig values, we're actually able to find the other ones. It's kind of neat. Anyway, we'll stop that. That's going to be all for part 2.